Greetings, sentient beings, and welcome to the Punk Wyrks garage. Today, we're going to talk about fusion propulsion. If I'm going to talk about fusion propulsion, I need to touch up on a few things about the Discovery magnetic confinement fusion rocket that I didn't really cover in the last one, and we're also going to talk about our other fusion reactors here. I'm going to try to get through as many as I can. But first things first, I didn't quite show you that when you use this Discovery rocket there, you want to connect it to a thermal power generator so that it can sustain itself. You don't have to use, you can use other power to sustain it, but it will also sustain itself if you actually connect a generator to it. Okay. As far as its different reactor modes as well, Freethinker pointed out if you use deuterium-tritium fusion in this thing, when you have lithium present, you get quite the boost. This thing will suddenly produce quite a bit of power above what it needs to sustain itself. So you'll get like net power from the deuterium-tritium fusion. Helium is the byproduct, and lithium is very easy to come by. It's like, everywhere. You can also get it from fusion. There's like a fusion reaction where you have a lithium blanket around the fusion reactor, and so as you fuse materials and their byproducts slam into the lithium, it produces more fusion materials, which in turn, when they fuse, they form lithium, which can then just, the whole cycle just kind of repeats itself, and suddenly the lithium is a used up resource. It's like a catalyst resource or whatever. This one has a bunch of different modes, deuterium helium-3 being pretty simple. Spin polarized is pretty good too. But you get a lot of options. I think this one, the helium-3 catalyzed deuterium fusion, will produce tritium for you. So you produce tritium that way, and then you can go back and do the deuterium-tritium fusion and pick up some more helium-3 somewhere or something, and just keep doing that cycle. You get a lot of options. So why am I showing you this thing? All right, well, if I'm going to show you fusion, I want to show you I want to do a build. So I'm going to kind of show you this, and then if you look here, fuel tank, radiator, that's some rocket parts. We can get rid of that. Let's just take that whole thing off. You can put whatever you want as far as cargo. That's just, control and that sort of thing. There's a refrigerator right there. None of this really matters right here, right? So we can just take that whole thing off. And now we're left with our propulsion section. So right here, I got graphene radiator, normal size. So we'll just take that off. Definitely when you're working with radiators, giving your craft a mohawk will make it look cool. I don't know how it affects the performance, but it certainly looks cool. Let's see. Oh yeah, actually I'll leave this on for the time being, because just for a second. What's in here? There's lithium in here, and this tank has helium-3. This tank has hydrogen gas, and this has deuterium gas, and then I have storage for tritium gas in these containers right here. Not filled up, just so I can, to give the idea that I would be intending on breeding more tritium before I started using it. The Discovery engine, deuterium and helium, is stored in there. And then right here I got a positron antimatter reactor at 1.4. All right, I scaled it up a little bit because I wanted to get just in that sweet spot of the raw power that I wanted on this thing, and I have 2 of them. That way, when I'm charging my warp drive, it's nice and smooth without needing too much radiator power. Just enough to charge it at the rate that I want it to charge, without being overkill and then needing more radiators. It was the idea there. So it took a minute, to get to the 1.4 spot. It took a while to find that. So yeah, let me just take the warp drive off. Oh wait, hang on. See, I gotta find So there's that, and then there's that. Alright, so let's take the ring off. There's that. There we go. Okay, got the warp drive. Take all that off. And that. And these. Okay, and now we're down to the rocket and the thermal power generator. So you saw how all that went. So let's build something right back up. Rightio then. So Jet Propulsion 101. The most basic way I can put it, I'm not like, you know, any sort of engineer or anything. I'm just some punk kid, like, well, that's like a gazillion years old, but that's still a kid. Not a kid, YouTube. I'm just saying, in the grand galactic scheme of things, we're all very, very young, comparatively, you know. Okay. Anyway, we eat things that are older than us, as someone has pointed out recently. You get your fusion reactor, and it doesn't really matter how hot you get it. What really matters is how much you can compress that air. So what you want is your best air intake. As far as stock KSP goes, that's going to be your shock cone intake. Because if you look here, you know, intake area 0.75 square meters. That's great. And effective base speed 5 meters per second. Well, what does that mean? Well, I'm not going to really be able to give you too much on the math of that, but if we compare that to other intakes, we notice that the crappiest intakes, or the lower altitude, I should say, intakes, have effective base speed of 15. So that's the radial air take. The small ones also 15. And if we go up here, we look at this divertless supersonic, and we scroll to the bottom, 12. So it's, you know, better than the bottom ones, but this one's at a 12. If we look at this one, 15 for the big circular one. If we look at these guys up here, 10 for the adjustable ramp intake, and the radial adjustable ramp intake also 10. Okay, but if we look at our shock cone intake, 5 meters per second. So what does all that mean? Well, when you're running a jet, unlike a rocket, when you're running a jet, you're basically trying to perpetually fill up and deflate a balloon. But what you're trying to do, what you're trying to do is take cold, slow, dense air, gather as much of it as you can, and then squeeze it out the back as hot, you know, spare, fast-moving air. Say a la thermal nozzle. Don't worry about these. I just got some weird debugging on. Everything's fine. Now, what you're going to get when you're at high altitudes is air that is already spare. It's already sparse. It's not very dense. It's going to be hot because you're moving through it really, really fast. So that's going to heat it up, and it's going to be moving fast because you're moving fast. So if you've got your air that's already hot, spare, and moving fast, and you're trying to compress it, heat it, and then squeeze it out the back, moving hotter, faster, and even more spare, you're going to encounter a challenge in that you can't. So it is more ideal when you're up at high altitudes flying really fast and it's really hot to compress that air down before you get it to your heat exchanger. So your best bet with that is your shock cone intake, unless you have magical modified air intakes. The shock cone intake will slam into that wall of air and slow it down, also cooling it off, and it will compress it so that when your air comes in all hot and spare and, you know, moving fast, it gets slowed down, cooled off, densed up, and then you heat it up and spit it back out. Okay, so when you're making those high altitude vessels, if you don't have a shock cone intake on there, because that's the first thing I ask you, what kind of air intake are you using? And you're going to be like, well, the meter says I'm not running out of air, and I'm going to say that doesn't matter. I want to know what air intake you're using, because I want to know how fast the air you're encountering is being cooled down and slowed down before it hits your heat exchanger. Okay, so use your shock cone intake. You can make a big one. Okay, so Great thing about these is they also work at slow speeds too. They're your arrow spike on the front, if you will. You could also do something like that. Keep in mind you're going to need radiators and a generator and such, so this thing alone won't fly. But basically, this is what you're looking for, okay? Aside from everything else, you want intake that's ideal for high altitude flight, that's going really fast, and you want to spit it out after you've done that. Now you might think pre-cooler. A pre-cooler is a great idea. Where is the pre-cooler? There's the pre-cooler. Okay. Boom. Now you have a pre-cooler. Now you can go even faster, ideally. I don't know, I'm getting some null value exception. Doesn't really like what's going on here, I guess. Let's see. Probably need a generator. That. There's that. Let's do some thermal. We're just going to run a test real quick and see what happens. This, by the way, folks, is how I develop. All right, I start from scratch and I just test things out, test my theories out. You know, there's theory and then there's, you know, application. So I have a theory about how things should work, and then I try it out. Let's see, we don't have any proper fuels, so let's just go with hydrogen. And on board. Yeah. All right, let's see if it launches. Oh, it doesn't have control. Okay, let's put a probe core on it. I have a radial attached probe core. That's handy. Okay, let's launch. Okay, here we are on the launch pad, and yeah, let's find out if any of this is even going to work. Stage our engine, open up our meters. There we go. Okay, can we see everything? I think so. Radio. Thermal power, that's what we want to look at right here. Right there, thermal power. The rest of these are incidental. Okay. Liquid hydrogen for the fuel is being stored in the engine pre-cooler thanks to fuel switch, allowing us to do that. And resting, let's see, air per second, 280, effective airspeed, 5 meters per second. Oh yeah. Okay, so we'll just go ahead and leave this open. And then arrow spike. Let's see. Next propellant, liquid hydrogen. Oh, right, because we're not. Okay, so let's not worry about that. Okay, let's just look at hydrogen real quick through the toroidal arrow spike. Oh, that went really quick. Let me restart that. Okay, take two. 1,600 units of liquid hydrogen in the atmosphere, sea level-ish. Toroidal aerospike engine. I got the reactor open this time, so you might be able to catch a glimpse of what's going on. And let's open these. And thermal power. There we go. All right, so I'm going to do it again. 3, 2, 1, and fire. 713 kilonewtons for, like, 2 seconds. But yeah, that's in atmosphere, so you'd need a lot of hydrogen if you were going to launch that way using that, but that would, if you had enough hydrogen, that would do it. All right, so let's try something real quick. Just out of morbid curiosity. Oh well, yeah. Okay, let's try something else. I see an issue. right then. Okay, so let's try this again with a turbojet engine, shall we? Go ahead and open these, and that, and that. Okay. There we go. Take 3. Oh, that was not what I wanted. Okie dokie. And yeah, take 4. Right. So air intake is what we're using. Shot cone tells me we're getting 280 air per second, effective airspeed 5 meters per second. Thrust out the back 1,904.9 kilonewtons. This is with the 2.5 meter magnetized target fusion reactor, 2.5 meter thermal power generator, and a pre-cooler and shot cone intake of the same diameter. And then, of course, excessive amount of radiation or radiator power. But as you can see through this simple test, and this is this is how I hear the big wigs, the pros, they test their rockets out. They put it up on a stilt and they fire it and make sure it works without flying off somewhere. Right? That's totally how it works. That's exactly how they do it, I'm sure. Okay, cool. But what can we do with that, What can we really do with that? We don't really need radiators nearly this big, so what if we went smaller? Like that big? Okay, that's a start. Maybe we turn them around. Okay, that looks kind of neat. I'm digging it. It's going to be a space plane, though, so we're probably going to need to put wings in place of these. So let's offset these a little. There. And there. That way we can put a wing directly underneath. And pretend that the wing is part of the radiator. I guess. We could do that. We could also do that. So, if you can see where I'm kind of getting here, the idea is to use your radiators as your lifting surface. So yeah, if you got your radiators as your lifting surface, you're saving on mass and doing yourself some favors at the same time. All right, so we still have quite a bit to go, but we also need to build a craft out of this. So let's check a few things here. Center of mass, center of lift. As you can see, these radiators provide lift, which is awesome. And center of thrust. Okay, so let's go ahead and let's see, do that and that. And don't really want a flag on there. We're going to do a flagless mission. Okay. Thinking cargo. Let's see, what kind of cargo do we want to carry? Basic or extended? Let's go with extended. All right, so we're going to need an adapter. I think I have adapters here. Not much in the way of Mark II adapters. Maybe I can... No? No? Aha, there we are. Yeah. This one. Okay, so stock says that's my go-to. And that looks kind of funny, but I think I can make it work. It's kind of the issue with getting this to work with Mark II, because immediately my instinct is to scale this down, but as soon as I scale it down, it's not going to be nearly as effective. In fact, let's do that first. Okay, I'm gonna go ahead and scale it down just so I can show instead of tell. Okay, so let's make it 1.25 just to have fun. Make everything else equivalent. So now we have very little to really worry about. Yeah, see, that's going to be more than enough. That there. Okay. Yeah. No. Needs a probe. Yep. Probe. If you don't have a mod that gives you a radially attached probe core, I highly recommend getting one. I get this one from Kerbal Planetary Base Systems, and I can't tell you how useful it is. It's so useful. So useful. Right, okay, so now our micro test. Let's get our hickey-doo-ha, and hammer-hammer-he, and this one right here. Let's put that right there, and let's make sure we don't crash. 2, 1, and fire. Okay, so now as you can see, we have quite a bit of difference in thrust. 238.1 kilonewtons is what we are getting right here at sea level. 70 air per second at 5 meters per second. Okay, so this is all the 1.25. So as you can see, we scale this down, and suddenly we don't have nearly as much power as we used to. I mean, we had 2,000 or something, yeah, so almost 2,000 kilonewtons of thrust when this was at 2.5 meters, half the size, and it is not half the thrust. It is a tenth, a little more than a tenth the thrust. So in fusion, size matters. If you don't believe me, ask any star. Size matters a lot. But yeah, so if we were to scale this down to fit into, say, a Mark II form factor, you can see that we're going to run into a lot of thrust issues. On the bright side, it is taking only 71% of this reactor's power, and it can essentially do this all day long, but we're already getting a little bit of embrittlement, and that embrittlement is climbing. So, take from this what you will. When you're building your space planes, keep in mind that making them miniature microfusion reactors, it's cool in sci-fi, but you gotta balance those issues. Okay, it does look super awesome, though, doesn't it? It's pretty cool. Okay, let's get back to the drawing board. Do 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 do. do 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 do. Okay, there we go. Lovely. So I like hydrogen peroxide, HTP, high test peroxide. It is 2 H's and 2 O's. It is good stuff for rocket fuel. It is, in my opinion, the best. Not because it has the best performance, or because it's the lightest, or it's the cheapest, or because it's the heaviest, or the most expensive, or because it's the most thrust weight. None of these individual things make it the best, in my opinion. In my opinion, it is the best because it is the easiest to make, and you get a huge bang for your buck for how little energy you have to put into producing it. So in my opinion, chemical reactions are energy transfer. A chemical is energy storage, and when you react it, you are transferring energy. And when you want that energy transfer to power, say, a rocket, you want it to be as cheap as possible. So you make this stuff from water, okay? Hydrogen and oxygen. It doesn't even have to be water. It just has to be hydrogen and oxygen. Readily available from water. But if you don't have actual water, you can get those hydrogen and oxygen atoms from anywhere that you happen to have matter. You're going to have a high probability of running into those two atoms in general. So you take those two, you smash them together using a little bit of electricity, basically, to get that one extra oxygen into the ring. It's actually like a cup. It's like an OHHO, something like that. Anyway, the chemistry of it, besides, you just get those atoms, you throw in some electricity, and you have a rocket fuel that explodes because it's unstable. That extra oxygen wants to go away. It wants to break down on its own. And if you give it a reason to, by shaking it violently, say with a fusion reactor, it comes apart pretty violently and releases a tremendous amount of energy, which then actually makes its constituent parts react back into water and release even more energy, which can eventually blow it. Anyway, you kind of get almost a double reaction out of it, and it looks super cool, and it's easy to make, and it's cheap, so everything else aside, just because of that, it's, in my opinion, the best. Anyway, we're going to use that as our propellant. I'm going to stop talking so much about that and just go ahead and get the show on the road. Make these teeny weeny high test peroxide, and then right. Let's I didn't do this right. Okay, let me try this again. One of those there. It's there. That. Certainly. Okay. That works for me. A little bit of control surface, perhaps. That. Didn't quite get that there. Hang on. Okay. Now, if you made it this far into the video and you're wondering why I'm going into such gruesome detail, it's by request. I've been told that people want to see a little bit more in-depth builds that I do instead of just showing you the finished product. And I couldn't agree more. I feel that people's time is valuable, and I don't want to take up too much of your time. But if you want me to do this, I will absolutely do this. Now, as you can see, we have a perfect plane. Center of mass, center of lift, thrust, all of this aligns wonderfully. You saw me just build this, but this is just using the basic principles of what I understand of aircraft design, which is not much, You just balance it. You put everything to where you know where your center of mass is, and you keep an eye on where you want that center of lift. So our center of lift is basically, this is a lifting surface, this is a lifting surface, that, and that. So these two are balanced by this. These are in the middle. Everything else, then we got a little bit of a reaction wheel in the front. That's it, folks. For the final step, go ahead and point it upwards. It's a word, if you're familiar, upwards. There we go. And away we go. And here we are. Upwards test flight. I guess we'll go take one. We're going to start off in atmospheric intake mode and test thrust. 238.1 kilonewtons. Air per second, 70. Looking pretty good. All right, releasing launch clamps in 3, 2, 1. Alrighty, and away she goes. I'm just going to let it fly at its desired angle. I'm pretty much just going to let it do whatever it wants. Oh, well, I guess this will be a very short flight. The probe core right here is what is responsible for that. So whenever you have stuff like this, it's going to orient itself like this because this is now pulling down. If you know about wings, having this up produces lift in that direction, but since we don't have much control, it wants to go to lowest energy state, which is towards the ground. Which is why it orients itself with the heaviest part to the ground. It's also lift, reverse lift towards the ground is what's going on there. And that's about that. Okay, cool. Okay, so one thing, we get rid of that top-mounted probe and put an inline probe. Thing 2. You're going to enjoy this one. We install what I like to refer to as ballast. Now, as you can see, I'm not really covering interstellar stuff at this point. I'm just covering you know, spaceplane design, how to make the interstellar engine into a spaceplane, and you have to do a few things. So let's see, we did that, so that probably moved center of lift and mass. Let me pull to you, put that, and that. Alright, so now we're a little like that. So what we need this a little more forward. Right. I guess that's about as good as right there. Try to move these back a little. We'd have to put them pretty far back. Okay, so since that's not going to work, because if you put these back here, they won't get as much air. So you kind of want to make sure you're not pushed too far back. We could actually live with this. This isn't the worst. But I do. I do feel I should make it a little heavier in the back. So what I'm going to do get some control surface, or some control things. Is that... Closer. That's pretty good. That's pretty good. A little... No, that's good. Okay, let's try this one out. See what happens. Okay, alright, back for another take. Gonna try this one again. Little modifications for stability, and yeah, we'll see if this works. Now you might be thinking, why am I not showing you other fuels? Clearly these use all sorts of different fuels. Why am I not showing you that? Well, if we're focusing on space planes, if we're focusing on single stage to orbit, if you're not using your atmosphere, you're doing it wrong. Okay, I don't mean to be rude, but if you want a single stage to orbit using these engines, use atmosphere as your propellant, because a planet's a pretty big fuel tank. If you're using chemical propulsion to get out of the atmosphere, you use when you have you know, the thermal turbojet available, you're doing it wrong. As soon as you get the thermal turbojet, your fuel use should be like destroyed. Like, you shouldn't really be thinking in terms of what fuel should I use. You should be thinking in terms of what's the best reactor to get the best performance out of atmosphere. Once you're out of the atmosphere, then your fuel choice is based on what is readily available. So if you have nearby atmospheres to gather fuels from or whatever, then that's what you use for your fuel. Use whatever it takes. Use argon, use carbon monoxide, use carbon dioxide, use helium, use hydrogen, use whatever. That these things will burn. These different engines will burn different fuels, and we'll get to those once we're out in space. Anyway, here we go. All right. So we spool up 238.1 kilonewtons, and we launch it, and it takes itself up. We're going to go ahead and not touch the controls, and we can already tell it's doing much, much better. That is what ballast does. Okay, that's what I call ballast. That is what makes your plane not do silly stuff. Okay, so it's just going to keep on doing what it's doing. Now you notice it's not even broken the sound barrier yet, and I don't expect it to, because this is too puny of an engine to get anything meaningful from. We're up to 309.7. We're starting to lose thrust. Let's see, effective airspeed is 333 meters per second and climbing. So it's a little bit faster than we're moving, which means that when we spit it back out, you know, it's going to be for less and less thrust. Okay, and that's just a sad fact of how this is going to work, because there's only so much you can do. Now, if you're light and aerodynamic and not producing a lot of drag, you can take advantage of that. You get to a certain altitude, you build up a certain amount of speed, and eventually you gain enough speed to meet orbit, and that'll take place at different altitudes. So let's say we're at about 6,000, we level off to try to start gaining speed. So we're picking up speed, and eventually we'll get going fast enough. In previous spaceplane videos you might have seen me do, my favorite technique is to come from the runway and do this acceleration portion at sea level. Get up to about Mach 3 and then bank up very steeply to fly out of the atmosphere, since I only have to get about 30 kilometers up. If I'm moving at 1,000 meters per second, that gives me 30 seconds to get there, which means that if I lose 10 meters per second, 30 seconds, you know, it's gonna take longer than 30 seconds, but I will still get pretty close before I run out of momentum, you know, just on its own. Plus I got an engine behind me slowing that rate of decay of velocity down. So the idea is basically go Mach 3 at sea level, bank steeply, and get to space before I run out of that stored up velocity. Doing it the slow way is getting up to altitude and then slowly getting up to like Mach 3 and then doing the same thing. It's just so much easier to do at sea level. Now if I miss that, if I try to do that at sea level and I don't gain enough velocity, then I won't be able to get to space and I'll have to abort and start over. But as you can see, with something like this, we will go until we run out of fusion materials, which will happen in about 74 minutes. So we don't have, forever to do this. Now I could switch fusion modes, do cold deuterium, and let's see. Oh, we're actually getting a little more. Let me go back. So about half the thrust, but it's climbing instead of, oh no, it's leveling off again. Okay, it's starting to go down again. So that doesn't help us. How about deuterium? Nope. Deuterium, tritium's our go-to for that. Everything else, not enough thrust to weight ratio to get us out of the atmosphere. Okay, so this is clearly not going to get us to space. For the exact same reasons that you probably run into, you just run out of thrust at this altitude, and you're not going to be able to gain the momentum that you need. And I can sympathize. This is not going to work. Okay, so let's try this again at about 3.5 kilometers. Yeah, 3.5 kilometers. Let's see if we can get any better speed out of this. Now see, this is slowing us down because the air is much, much thicker. And we're still only producing 291 kilonewtons of thrust. So we're going to reach a point of terminal velocity before we push through that. So also not exactly ideal. Yeah, see, 338 meters per second, and we are not budging. So this just isn't going to do it. I mean, you can make some cool stuff, but within a reactor this small, you just can't expect space from that. I'm sorry, but it's just not going to do it. It just doesn't have the oomph. However, if you want to do this with chemical propulsion up in the atmosphere, then this becomes handy. I mean, we didn't carry all this fuel for nothing. Okay? So, when atmosphere isn't going to take you to space, but it'll certainly get you close, here's what we do. Okay? Go ahead and angle up a little bit. It's going to take a minute. Again, I apologize for the lengthy video, but I want to really go into depth on these things, and I could spend hours on each individual engine and each individual mode and the ins and the outs and the goods and the bads. But here we're just going through step by step as if we were learning how to space plane for the first time. Okay, now if your ear's good, you kind of hear that whine where it starts to get the air starts to get a little rarefied. Okay, we're only at like 12,000, so we're not even like close to space yet. But we still got 173 kilonewtons, so we're gonna keep going. Okay, we're just going to keep going. Oh yeah, we're losing air quick. If you see right here, air per second, it's dropping, it's dropping. Air speed, however, keeps climbing, which is why we don't have the thrust that we need. Okay. All right, we're dropping below 100 kilonewtons, but we're at about 20,000. Okay, so here's where everyone else's engines just give out, because we see that decay is pretty bad. But if you've got enough momentum behind you, you're going to climb through that 20K mark just from the momentum behind you. We haven't slowed down enough yet. Okay, we're still gaining surface speed. Our vector is about 20 degrees from the 19. Okay, here we go. What we do at this point is we switch propellants. I don't want this thing to explode. Right, atmospheric, hydrogen peroxide. Alrighty. Activate. Okay, hydrogen peroxide. We're back at 178.6 kilonewtons because we're still in atmosphere, but that will give us more than enough. That's 2 G's right there behind us. It's going to give us more than enough to push us out into the atmosphere. The amount that we have, we started with 1,875 units. We're using about 15 a second. So we don't have a lot. But if we look at our apoapsis, and this isn't the best ascent, I suppose. Let me go to about 20 degrees. Apoapsis 52. So yeah. Go ahead and level off. Oops. Okay, I kind of overshot that one a little. Shot cone intakes, hydrogen peroxide, and we got to space with the 1.25 meter fusion reactor. However, as you saw, we didn't do it with just the atmosphere. We got up into the atmosphere using atmospheric intake. We had to switch to a healthy amount of hydrogen peroxide to get the rest of the way. Let's see if we have enough to actually circularize. Says we need about 460 meters per second. And go. Let's see, 179.1 kilonewtons out in space. And what do you know? We have circularized and we still have 702 units left. Ta-da! Cool stuff. You can use nitrogen, you can use, I mean, different ones have different things, so I can't really list them all off the top of my head. I just know that when I use the thermal turbojet, when Punk Wyrks is running the show, it's atmospheric intake and hydrogen peroxide, and you can forget the rest. Other engines, it's usually liquid hydrogen is what I use. The other fancy fuels and stuff, such I don't use them a whole lot. I'll use argon, CO2, oxygen, and nitrogen when those gases are readily available in an atmosphere. And yeah, so I'll harvest the atmosphere, and then that's what I use to propel myself around space. Because they're great. Argon is a good one. Lithium. Lithium is an excellent electric propellant. Yeah. It's not an electric engine, so it doesn't really help us here. But I hope this gets you some clues on space planing with a fusion engine. You got to brute force it, you know. You get as far as you can with atmosphere, using the best atmospheric intake you can. Idea behind the atmospheric intake is you want it to slow the air down, because the faster that air is moving, the less thrust you can get out of it, as you hopefully saw in these two readouts here. As airspeed rose, thrust dropped. That's all I can say. That happens. And then you just switch to your onboard chemical propellant. You reduce drag as much as possible, and you improve stability by just understanding, how a wing works. When you've got a wing, it's curved so that you've got, varying degrees of surface area on the top or bottom of the wing. So if you've got a flat wing on the bottom and a curve, it curves up on the top, you're producing lift up. Okay. So if your vessel isn't stable and you have a lot of stuff up top, it's going to flip over to the bottom. So what you do is you make sure you got a lot of lift, and then you put something on the bottom that is actually going to keep the bottom of your craft pointed down. That's why you see a lot of planes, some planes, they'll have engines up top, okay? But they'll also have a really big bulky section on the bottom. Other planes you'll see with the wings strapped to the top of the plane, and it's got a big bulky section on the bottom holding it down. Other planes you'll see the wings underneath, but you'll notice that its entire lifting surface is lifting that up, and then the body itself that's lifting up is also a lifting surface, and it does some weird stuff to keep it from flipping over, but that also allows them to flip over very, very well. So what we did here is we just put some hollow tubes and intakes on the bottom to produce a little bit of downward force to keep the bottom of the craft pointed down, to keep it balanced at all times, and it worked really, really effectively. And then we got up to about 20,000, and then we kicked in chemical propellant to get us the rest of the way, using hydrogen peroxide, because it's not super light, but it's pretty light. And let's see, I think 0.7 tons for that tube, 0.3 for that one, so 2.6 tons of hydrogen peroxide, 2,600 kilograms of hydrogen peroxide. Our vessel mass was 6,000 kilograms, 6,420 kilograms. So, a decent chunk of the vessel mass, but not the entire vessel mass. So that's pretty cool. So from there, you can take a look at our spare fuel. We're in orbit with this vessel, and we've got 702 units of hydrogen peroxide left, which is more than enough to deorbit, but also not enough to go to, say, the moon. So you can add additional things to this, keeping in mind, the more weight, the less, delta V you're going to have. Also drag. So if you have things sticking out all over, it's going to seriously affect your aerodynamic profile, etc., etc. Okay. That's enough for this one. Let me know. I know this wasn't like the super cool space plane you thought you were going to get, but what I really try to show is not so much how to build the best planes, but how to use the principles of this mod to make a plane. So here's how this engine works, and if you use the 2.5 meter one, you get 2 tons of thrust out the back, and you can put a much bigger plane into orbit, but you're still going to have to switch to a chemical propellant at a certain altitude based on the cross-section of your craft. So if I build a craft and you build a craft differently, they're going to fly differently. It's just kind of how it's going to be. The real issue with the Mark II form factor cockpit is that it doesn't fit with the 2.5 meter fusion engine, which means you're going to have a lot of drag, and whatever adapters or whatever you're going to use is going to add mass, and it's not going to work very well. So if you use the smaller version, you're not going to have nearly as much thrust. So it's more stuff to deal with. What I would recommend is use more engines and reactors. Like use 2 of these reactors instead of just 1. Use 4 of them. Whatever you got to do.